Hello everyone, welcome to Qubit classes. In this video, we will study the matrix algebra using a couple of problems. So briefly, we will go through the outline. We will see what a matrix is. We will see what is an order of a matrix, what are the elements of a matrix. Then we will see how the matrix is represented, how to get a transpose of a matrix and a determinant of the matrix. We will also see how to add two matrices and how to subtract them. Also the necessary condition for two matrices to be added or subtracted. We will also see scalar multiplication of matrices as well as the vector multiplication. And we will study these concepts by solving problems. So consider the first problem. Let A be the matrix 1 3 6 minus 4 3 0 2 minus 1 11 and 6 minus 6 8. Find the order of A. Specify the row and column number of negative elements of A. Now, a matrix is a rectangular arrangement of numbers. These horizontal sequences are known as rows, and these vertical sequences are known as columns. So, any element of a matrix belongs to one row and one column. So, number of rows in A are 1, 2, 3 and 4. Similarly, the number of columns in A are 1, 2 and 3. Now the order of a matrix is defined as the number of rows times the number of columns. So in this case, the order will be 4 by 3. Also note that if there are 4 rows and 3 columns, the total elements or the total entries present in that matrix is 12. So if the order is m cross n, then the total elements in that matrix will be m into n. So we have specified the order. Now consider the negative elements of A, which are minus 4, minus 1, minus 11 and minus 6 respectively. Now the element minus 4 is present in the second row and first column. This is represented symbolically as small a 2 1, and this is read as a 2 1 is minus 4. Let's move on to minus 1. This element is present in the third row and second column, so it will be represented as a32. The next element is minus 11, which is present in the third row and third column. So it will be a33. Similarly, minus 6 is present in the fourth row and second column, so it will be a42. So we have specified the row and column number of all negative elements of A. Let's move on to problem number 2. Construct a matrix A2 2 by 3 such that Aij is equal to I by j. Now in the previous problem we saw that Aij represents the element which is present in the ith row and jth column of the matrix. We also saw that if the order of A is 2 by 3, it will have 2 rows and 3 columns in it. Also, the number of elements will be 2 into 3, that is 6. Yes, so Aij is the element in ith row and jth column. Now, let us symbolically write down the elements of A. So A will be A11, A12 and A13. These are the elements in the first row. Then in the second row we will have A21, A22 and A23. Now the condition in the problem is that Aij must be equal to I comma j. So A11 will be 1 upon 1, A12 will be 1 upon 2, A13 will be 1 upon 3, A21 will be 2 by 1 and so on. So we are dividing the row number by the column number of that element. So on simplifying, 1 upon 1 and 2 upon 2 will give us 1. 2 upon 1 will be an integer 2, and 1 upon 2 1 by 3 and 2 by 3 will remain as it is. So we have constructed a matrix which contains 2 rows and 3 columns, and its elements satisfy this condition. Aij is equal to I by j. Problem number 3. Consider A. Is it symmetric? Obtain its transpose and check whether it is singular. So A reads 1, 2, minus 5, 2, minus 3, 4 and minus 5, 4, 9. Now A has 3 rows and 3 columns. A matrix whose number of rows is equal to number of columns is known as a square matrix. So A is a square matrix of order 3 or 3 by 3. Now we want to check whether this matrix is symmetric. Now the condition for a matrix to be symmetric is this: Aij is equal to Aji. This means the element which is present in the ith row and jth column of a matrix must be equal to the element which is present in the jth row and ith column. Now the elements which are there along this diagonal, these are 1, minus 3 and 9, whose row number and column number are equal. For example, 1 is present in the first row and first column, minus 3 is present in the second row and second column, and 9 is present in the third row and third column. So these elements which are present along this diagonal, they always satisfy this condition because I is equal to j. So we will have to now check for the non-diagonal elements whether they satisfy this condition. Now if you look at A closely, you will see that the element which is there in the first row and second column, that is A12, and the element which is there in the second row and first column, which is A21, which is also 2, these are same. Next, let's move on to this minus type. This is present in the third row and first column, so it will be A31. Similarly, the element which is there in the first row and third column is minus 5. So A13 is equal to A31. Similarly, you can check it for 4. So A23 is equal to A32 equal to 4. Thus, all the elements of this matrix satisfy the condition for symmetry. Hence, this matrix is symmetric. Note that there exists another class of matrices which are known as skew-symmetric matrices. And a skew-symmetric matrix satisfies this condition: Aij is equal to minus Aji. So matrix A is symmetric. Now let's see how to obtain its transpose. Transpose of a matrix is defined by the matrix which is obtained on interchanging of rows and columns of that matrix. So transpose of A will be a matrix whose rows will be equal to the columns of A and whose columns will be equal to the rows of A. Thus, first row will become first column and first column will become first row. So you will see that statements mean one and the same thing. And A transpose is denoted by this A and this T is denoted as a power. But note that it is not a power, it is transpose. Now since matrix A is symmetric, its rows and columns are identical. So when you replace this first row, which is 1, 2, minus 5, by its column 1, 2, minus 5, you will again get the first row. Same applies for this 2, minus 3, 4, 2, minus 3, 4, minus 5, 4, 9 and minus 5, 4, 9. Thus we have obtained the transpose of this matrix. Now the last part is to verify whether the or to check whether the matrix is singular. Now let's again recall this thing that A has equal number of rows and columns, hence A is a square matrix. Now in general, a square matrix M is singular if determinant of M is equal to 0. Now I assume that you have some background of determinants and how to evaluate them. So this is a determinant of A will be a 3 by 3 determinant, and generally determinants are written, or the elements of the determinant are written between two vertical lines. Now this determinant is evaluated as follows. You will have to evaluate 3 smaller determinants to evaluate A. So this will be 1 into this determinant minus 3, 4, 4, 9 minus, note this minus sign, minus 2 into 2, 4, minus 5 and 9 plus this minus 5 into 2, minus 3, minus 5 and 4. That means we have covered all the elements which are there in the first row, and we have multiplied that element by a determinant formed by eliminating the row and column containing that element. For example, for this element 1, it is present in the first column and first row. So on eliminating this, we get minus 3, 4 and 4, 9. Similarly, for 2, we have 2, 4, minus 5 and 9. And for minus 5, we have 2, minus 3, minus 5 and 4. So this is a 2 by 2 determinant, this one and this one. Now a 2 by 2 determinant is evaluated as follows. You'll have to multiply minus 3 with 9 and you will have to subtract 4 into 4 from that answer. So it will be minus 27 minus 16. Similarly, this determinant will be 18 minus 20 and this determinant will be 8 minus 15. So on simplifying this, you will get minus 43 minus 76 plus 35, which is equal to minus 84. Now the condition for a square matrix to be singular is its determinant must be 0, which is not the case. Hence A is not a singular matrix. Let's move on to problem number 4. If A is 3 minus 2, 5, 4, B is 1, 4, 6 minus 7, find A into B minus B into A plus 4 into I. Now we will first see how to multiply two matrices. Let's see the first part, which is A into B. So I have written down the matrix A and matrix B. Now to perform matrix multiplication, we will have to proceed like this. Consider first row of the first matrix and first column of the second matrix. Multiply first element in the first column with first element in the first row. So you'll get 3 into 1. Into that product, you will have to add the product of -2 and 6. So you have taken the first row, you have taken the first column, and you have multiplied respective elements. That will give you the element which is there in the first row and first column of the product. Let's move on to the second element. To get this, you'll have to take the first row of the first matrix and second column of the second matrix, and you will have to multiply them element wise. So this entry will be 3 into 4 plus -2 into -7. Similarly, the third entry will be 5 into 1 plus 4 into 6, and the last entry will be 5 into 4 plus 4 into -7. I would like you to spend some more time on this matrix multiplication and how it is done. So 3 into 1 plus -2 into 6 will give us -9. 12 plus 14 will give us 26. 5 plus 24 will give us 29. And 20 minus 28 will give us -8. So we have now obtained A into B. Let's see B into A. Now the way matrix multiplication has been defined makes it impossible that A into B is equal to B into A. Generally, when you take two numbers, if you change their order, you will still get the same answer. For example, 5 into 6 is 30, but so is 6 into 5. But in general, A into B will not be equal to B into A. But if you follow the procedure which we did to get A into B, you will get B into A. So 23 will be 1 into 3 plus 4 into 5. It is 23. 1 into -2 plus 4 into 4 will be 14. 6 into 3 minus 7 into 5 will be -17. And 6 into -2 plus -7 into 4 will be -40. So note, we see that A into B is not equal to B into A. So this property is termed as, or rather we say that matrix multiplication is not commutative. But scalar multiplication or multiplying a number by another number is commutative, because on changing the order we still get the same result. So we have now obtained A into B and B into A. So the last part is 4i. Now the letter I is used to denote a specific class of matrices which are known as identity matrices. Identity matrices are square matrices whose all elements are equal to 0 except the diagonal ones, and the diagonal elements are equal to 1. Now 4 into I is another type of matrix multiplication where you multiply a matrix by a number or a scalar. So this is known as scalar multiplication. When you multiply a matrix by a scalar, you will have to multiply each and every element of that matrix with that scalar. So that will give us 4 into 1, 4 into 0, 4 into 0, 4 into 1, or 4, 0, 0, 4. Now in the previous slide we obtained AB and BA, and now we have obtained 4i. So let's find this expression. So AB is this, BA is this, and 4i is this. Note that order of each of these matrices is 2 by 2. Now matrix addition and subtraction are performed element wise. So the first element of this expression will be minus 9 minus 23 plus 4. The second element will be 26 minus 14 plus 0. The third element will be 29 minus 17 plus 0. And the fourth element will be minus 8 minus 40 plus 4. So on simplifying this, we will get minus 28, 12, 46 and 36. So we have successfully obtained this expression AB minus BA plus 4I. Problem number 5. Consider matrix A, which is 1 2 1 3 1 3, and matrix B, which is 2 3 1 2 1 2. Compute B transpose into A transpose and transpose of A into B. Now we saw in the previous problem that transpose of any matrix is obtained when you interchange its rows and columns. Now if B is 2 3 1 2 1 2, its transpose will be 2 3 will be the first column, 1 2 will be the second column, and 1 2 will be the third column. Similarly, A transpose will be 1 2 1 in the first column and 3 1 3 in the second column. So B transpose has order 2 by 3 and A transpose has the order 3 by 2. Now as we did for the case of matrix multiplication in the previous problem, we will take the first row of the first matrix and the first column of the first matrix, and we will perform element wise multiplication. That will give us the element which is there in the first row and first column. So it will be 2 into 1 plus 1 into 2 plus 1 into 1. Now let's find the element which is there in the first row and second column. It will be 2 into 3 plus 1 into 1 plus 1 into 3. Similarly, for the element in the second row and first column, we'll do 3 into 1 plus 2 into 2 plus 2 into 1. And for the last element, we'll do 3 into 3 plus 2 into 1 plus 2 into 3, which is written in this matrix. So on evaluating each of these expressions, you will get 5, 10, 9 and 17. Now for matrix multiplication, this property is very important. And that is, if matrix M is of the order P by Q and N is of the order R by S, then M into N is defined only when Q is equal to R. And when this condition is satisfied, which is the number of the number of columns in the first matrix is equal to the number of rows in the second matrix. If this condition is satisfied, then the product M into N will be of the order P into S. So in our case, P transpose was of the order 2 by 3 and A transpose was of the order 3 by 2. So Q is 3 and R is also 3. Hence, we can define this matrix multiplication. And the result will be P into S, which is a 2 by 2 matrix. Next. Now we have evaluated this B transpose into A transpose. Now we will find AB first and then we will take its transpose. Now as we did for B transpose into A transpose and the other cases of matrix multiplication, we will perform A into B in a similar fashion. So we'll take the first row and first column, first row and second column, second row and first column, and second row and second column. So I have written them down here. On simplifying, I will get 5, 9, 10 and 17. Now I have obtained AB, but what is asked is transpose of that matrix AB. So I will interchange its rows and columns. So 5 and 9 will go in the first column. 10 and 17 will go in the second column. So this will be B transpose into A transpose. Now this is an important result. If you have two matrices A and B, and you can define B transpose into A transpose, then the the transpose of their product is equal to the product of their transposes. In general, B transpose into A transpose will be equal to transpose of A into B whenever the products are well defined. So this is an important result. Problem number 6. If f of alpha is equal to cos alpha minus sin alpha 0, sin alpha cos alpha 0, 0, 0, 1, find f of minus alpha and f of alpha plus f of minus alpha. So in this case, this matrix itself is a function of alpha. Each element of this matrix depends on the value of alpha, at least the elements which contain the trigonometric functions. Nothing will happen to this 0, 0 and this one. So let us first find f of minus alpha. To find f of minus alpha, we will substitute minus alpha in the expression for the function or the equation. So f of minus alpha will be cos of minus alpha minus sin of minus alpha 0, sin of minus alpha cos of minus alpha 0, and this last row will be unchanged. Now if you have learnt about functions and their characteristics, you'll recall that sin theta is an odd function. That is, when theta is replaced by minus theta, so sin theta will become minus sin of minus theta, and this sin of minus theta becomes minus sin theta. This is the characteristic of an odd function. And cos theta is an even function. That is, if you replace theta with minus theta, you will still get the same result. So cos of minus theta is equal to cos theta. Now we'll use the properties of trigonometric functions to simplify this. So cos of minus alpha will be cos alpha, and sin of minus alpha will be minus sin alpha. Sin of minus alpha will be minus sin alpha. That minus sin and this minus sin will become plus. So you'll have sin alpha. For cos of minus alpha, you will still get cos alpha. So notice that f of minus alpha is actually a transpose of f of alpha, because the first row has now become first column, the second row has now become second column, and the third row has now become the third column. Now we have found f of minus alpha. Our next task is to get f of alpha plus f of minus alpha. So as we did previously, we will add these two matrices element wise. So cos alpha and cos alpha will give us 2 cos alpha. Minus sin alpha plus sin alpha will give us a 0. 0 plus 0 is 0. Even here you will get 0 because you have sin alpha and minus sin alpha. Cos alpha and cos alpha will become 2 cos alpha. These two terms will give you 0. So in the last row, you'll get 0, 0 and 2. This one and this one become 2. So I have taken this 2 common from all these elements. So we had 2 cos alpha, 2 cos alpha and 2, and all the other elements were 0. So you can take this 2 common from all these elements, which is a scalar. Now notice that you have all elements zeros except the diagonal elements. Hence, it is a diagonal matrix. So, we covered the concepts of a matrix, how it is represented, what is an order. Then we saw various types such as identity matrix, symmetric matrix, skew symmetric matrix, square matrix, and so on. We also saw how a transpose is defined. Then we solved a couple of problems on matrix addition, subtraction, scalar multiplication, and matrix multiplication. Note that division of two matrices is undefined. We have an operation which is similar to matrix division, which is known as finding inverse of a matrix, that we will see in the next video. We also saw what are the criteria for defining these operations, and these criteria have to do with the order. So two matrices can be added or subtracted only when they have same order. Two matrices can be multiplied only when the number of columns in the first matrix and the number of rows in the second matrix are same. And we also noted that matrix multiplication is not commutative generally. And if the matrix is a square matrix which contains equal number of rows and columns, you can define its determinant, which is a number. So, in the next video, we will see how to perform elementary transformations of a matrix, and using those transformations, how to find inverse of a matrix. So I think you have understood the matrix algebra. If you want more or have any queries, you can contact us at qubitclasses@gmail.com. And don't forget to hit like and subscribe to our channel. Thank you.